Honestly, if I didn't have to wait an entire year to take this class, I thought about it. Yeah, no, it's horrible. So that's what I'm thinking about for this exam.
If you took the second one and you bombed the first one and you realized you
That's true.
probably bombed it,
On the first one, you took the second one, you had no idea what you're doing. Okay, that makes sense. But, you know, I got an 80 on the first one. Survived with that.
Yeah, I'm just on for a 70. I'm just trying to pass now.
See, my only worry is if I get a 70 in this class, then I'm gonna get a fucking 50 in PChem 2. Because PChem 2 is supposedly hard.
Oh yeah, because I got a like an 80.3 in Cal 1, and I think I had like a 75 in Cal 2.
Cal 2 is so much worse than Cal 1. Yeah. So, I love calculus.
Oh, shoot. For OChem 1, I had to get an 80 on the final to pass the class with a 70. I got an 80 on the final. So, see, doing good.
That's my thing. Like, I want to be in this class. If I make a B in this class, I'm likely to make a C or B in PChem 2. I'm in the opposite.
I found that hard classes are actually easy. I don't know why.
All right.
Better in the hard class.
Okay. So for those here on Zoom, as I was saying to those in class, I have not started grading the exams, so I don't know how they've turned out, how they are, or anything of that nature. So, I'll have them graded for next week. So, see, otherwise, let's see here. Homework 5 has been posted. It's available online for you to look at. I know the due date for that is like a Wednesday instead of Friday or something like that. But yeah, so just keep in mind when the due date is. I'll remind you as we get closer to it. But so basically, 2 weeks from when we took the exam, this last Wednesday is when homework 5 is due. Again, it has been posted. All right. Trying to think any other kind of announcements. Yes, nothing else comes to mind. Any questions people have for me about anything? Particularly, Zoom here. Open up the chat as well in case someone. All right. Okay. So today we're going to be talking about activities. Just doing some examples with that, and then and we probably will end a little early today, but I'm not going to bother trying. We're already ahead of schedule, and we'll have plenty of time to potentially cover some extra little things at the end of the semester. So I'm not going to try to rush even more or anything like that. So today we're just going to cover this and stick with it. Right. First is just kind of a review question, right, of our colligative properties, right? If I want to compare to a 0.2 molar CH3OH solution, which of the following aqueous solutions has a higher freezing point? So people saying 1 here. Actually, in this case, it is none of the above, right? No, 1 forms a 0.3 molar solution, right? CH3OH is a weak acid, so it's not going to be anywhere close to 0.3 molar. It's going to be 0.2 something molar, right, worth of stuff in solution, right, since CH3OH, right, is a weak acid. And so all of the solutions listed, 1, 2, and 3, all have a net concentration greater than 0.3 even, right? And CH3OH itself is not going to get anywhere close to 0.3 just because it's a weak acid.
Right.
Question?
But if a weak acid dissociates more than 50%, then wouldn't it be above 0.3?
I mean, but I don't know of a weak acid that dissociates 50%.
Are we supposed to know that?
I mean,
I know the dissociation of every weak acid.
I guess, I don't know of a single acid. Like if something is a weak acid, right, its dissociation is a very small percent. And otherwise it's kind of a strong acid. There's not really a lot that's kind of in between. But I mean, that's part of the reason why this is just kind of a question in class, not necessarily a question on line or an exam or something like that, right? I'm not expecting you to remember all of your weak acid dissociation constants or things like that, right? But yeah. So in this case, it is just going to be none of these things. All of these solutions with barium chloride all have freezing points lower than the CH3OH solution, right? Because as you increase the concentration of your stuff, right, your freezing point drops further and further and further, right? Other questions? All right, so today, as I said, we're going to be talking about activities. Okay. So activity is basically something that we use sort of like we use the compression factor for ideal gases. Okay, so right, so if we have, right, again, some solution where I'm talking about the chemical potential of the solvent being compound A here in my mixture of compound A and B, right? Right, that change in chemical potential of the solvent is related with its change in vapor pressure of the solution versus, right, the vapor pressure of the pure solvent. Okay. Now, for an ideal solution, right, we would use Raoult's law, and we'd say, okay, that ratio of vapor pressures is just related to the mole fraction in the liquid phase, right, for an ideal solution. Okay. Right, and again, the reason why this is for Raoult's law for an ideal solution, right, is an ideal solution, all of your intermolecular forces are identical, right, between solute and solvent and solute, solute, and solvent, solvent, right? And so in that case, right, as your mole fraction of A decreases, right, what's happening is you just have less of A in solution, right, which means the vapor pressure is going to decrease accordingly, right? As I reduce the amount of stuff in solution, it's also going to have an equal reduction in the amount of stuff in the gas phase, right? Right, because that's effectively all that's happening for an ideal solution is that you add more and more solute, right? The amount of stuff in your total solution, right, becomes less and less of the solvent, right? Right, or of A, right? As I add more and more B, the total amount of stuff of A in solution decreases, and so its vapor pressure is accordingly going to decrease, right? Because I have less A that's going to be reaching the surface of that solution, right? And escaping into the gas phase, so there's going to be less gas phase molecules, right? So it's just kind of this linear relationship between the amount of stuff of A in solution and the pressure of A in the gas phase, right? And which is associated with the amount of stuff of A in the gas phase, right? The vapor pressure of A is just related with the number of moles of A in the gas phase. So the less, amount of stuff I have in the solution, the less I will have in the gas, right? So that's all an ideal solution is saying, right, is that the change in vapor pressure is purely due to the change in number of moles of your compound in the solution phase, right? It has nothing to do with intermolecular forces or anything else, right? And again, that's why it's considered kind of an ideal solution. It's like we also think of, say, ideal gases, right? Well, for a real solution, we instead call that ratio of pressures, vapor pressures, PA over PA star, the activity of A, okay, which you can think of as its effective mole fraction, right? So, and that's all basically we do with activities. Activities is an effective mole fraction basically that we define for a real system that is going to somehow incorporate all of the like non-ideal things going on in that real system. Okay, right? Sort of like, again, for the virial equation of state, you have like pressure times volume equals Z times nRT, where Z is your compression factor that you expand in terms of pressures or volumes, right? And that Z, that compression factor, incorporates all of the non-ideal behavior of the gas, even though you're using this still PV equals nRT kind of form of the ideal gas equation, right? All of the complicated crap is just swept into this Z term, right? This compression factor, right? And so similarly, right, for mole fractions or things like that, right? For real solution, right, we're going to just kind of sweep in all of the real effects into this activity, right? And again, we're just defining the activity as the ratio of the vapor pressure over the of the solution over the vapor pressure of the pure solvent. Okay. Right. And so basically, again, we're going to define the activity as PA over PA star, and then we're going to also relate it to the mole fraction, which is the ideal case, right? This activity is sort of the effective mole fraction, so we're going to relate it to the ideal mole fraction with this gamma sub A, which is your activity coefficient. So A is the activity, gamma is the activity coefficient, right? So if you see that word activity coefficient, it's referring to gamma, okay? And the activity itself is referring to A, right? And so the activity is just related to the activity coefficient times the mole fraction of A. And so then for a real solution, right, your change in chemical potential is related with the pure solvent chemical potential plus this ideal change, right? Raoult's law gave us RT ln, the mole fraction of A. And then we just add on this RT ln of gamma, which is essentially incorporating all of the non-ideal effects that are going on, right? So this activity coefficient is sort of like your compression factor, right? Where it's just sweeping in all this non-ideal effects into this thing, right? That we don't really have an expression for. Now we will, when we talk about electrolyte solutions and things like that, we'll talk about an expression for the mean activity, for the activity coefficient and things like that. But in general, it doesn't really have a functional form. And, you'd have to just say, determine what it is experimentally, right? If you wanted to, right? What gamma sub A is, right? And gamma sub A could depend on the mole fraction itself, right? It could depend on temperature. It could depend on a lot of things, right? Right. And so, right, it's potentially a complicated looking function and not necessarily just a constant. Now, we'll often just treat it as a constant, but yeah. And so again, right, for your solvent, right, your change in chemical potential is just related with the ideal change plus some real correction factor related with the natural log of the activity coefficient, right? And the limit of a dilute solution, right, you start to obey Raoult's law, because in a dilute solution, the mole fraction goes towards 1. The activity is going to go towards, is going to equal the mole fraction in a dilute solution. And then the activity coefficient is just going to equal 1 for an ideal solution. Okay. Again, for a dilute solution, right, you're going to approach an ideal solution for the solvent, and it's going to start obeying Raoult's law, and you'll have kind of the relationships down below. Okay. So the more dilute solution is, the closer the activity is to the actual mole fraction, right? And again, we'll see this when we talk when we talk about some expressions when dealing with electrolytes and calculating mean activity coefficients and things like that. But yeah. Yep. questions about what is the definition of the activity, what it means, what is the activity coefficient, anything like that? All right, for the solute, we basically do the same type of thing, right? Where we're, again, going to kind of relate that pressure of the solute over the pressure of the pure solute, right? The vapor pressure of the solute and the mixture and the vapor pressure of the pure solute, right? To the activity, okay? Which, again, is related with the activity coefficient times the mole fraction, right? So we have the exact same type of stuff, okay? I kind of swept in here, right, is the fact that for the solute, the ideal case is related with this mole fraction times Henry's law constant, right? The solute in a kind of an ideal dilute solution obeys Henry's law, not Raoult's law. And so there's this Henry's law constant thrown in there, but that's just a constant. And so it's not a typo to go from this mu b star, which is our pure solvent chemical potential, to mu b naught. Mu b naught is just the pure solvent chemical potential plus a term related with the natural log of Henry's law constant, okay, which again is just a constant, so it's just kind of adding some constant to this thing, right? So we just kind of sweep it in to the chemical potential of the solvent, okay, right? And we can do this just because often we care about, right, changes in things and whatnot. So when we take differences in chemical potentials, these chemical potentials, right, mu b star or mu b naught, these things will just cancel and never really appear. So we'll never really actually talk about what is the chemical potential of a pure solvent. Right, in this class, we'll never define what it is or compute it or anything else like that, right? It often goes away in whatever we're concerned about, right? Like we'll use these type of expressions when talking about, say, chemical equilibrium. And all of these chemical potentials will kind of go away in a sense when we deal with that. So, but that's for another day, right? So again, you have now again the activity for a for the solute, right, is in related with its vapor pressure in the mixture divided by not the pure solvent vapor pressure, but instead the Henry's law constant, right? Okay, and again, that's just because for a dilute solution, okay, this solute should obey Henry's law, okay? And so in order for the activity to eventually equal the mole fraction, right, if this obeys Henry's law, then PB equals the mole fraction times KB, and so then A will equal the mole fraction, okay? Right, so again, in a dilute solution, when the vapor pressure can be approximated by Henry's law, this equation here, AB equaling PB divided by KB, will simplify down to AB equals XB, right? Right. But if I used PB star here, then that wouldn't simplify down. I'd get XB times, or let's see, it'd be XB times KB divided by PB star or something like that. I'm gonna write that stuff out if people want me to kind of see what I'm talking about. I know I'm saying things and not necessarily writing it out, but right. And then again, right, the activity is related to the activity coefficient times the mole fraction of the solid. So questions about kind of the stuff on this slide. Okay. Again, the main point is the activity is just essentially the effective mole fraction, and our change in chemical potential is just related to the ideal change plus some correction from non-ideal stuff, which is related with the activity coefficient. All right. Now, often in solute, right, we deal with molalities of the solute, right, not just mole fraction. Okay. So to do that, right, basically what happens to the equation is instead of having a mole fraction here, we have the molality. And in order to like get from one to the other, you have to kind of modify this chemical potential by like the natural log of some molecular weights and crap like that, right? So again, we just kind of sweep in the effect of changing these units and things like that into the kind of pure solvent chemical potential, if you will, right? But it's so this mu B naught is the chemical potential of the solute in a concentration of 1 molal. Okay. So that's actually what mu B naught is. Okay. So it's a concentration of 1 molal, right? And so for solutes, when we're dealing with molality, which is more often what we're dealing with, right? Again, we have this chemical potential here, right, which is related with the activity, is then defined as the molality divided by the 1 molal times the activity coefficient here. Okay, the activity is still a unitless quantity, so that's why the activity here has this divided by B naught here, 1 molal, to make this thing unitless. Okay, right. And again, you could then plug this back into the equation above to kind of get that the chemical potential is, again, the ideal case related with molality plus some correction term, right, related to the mean activity coefficient. Yeah. But yeah, and again, for ideal dilute solutions, right, as the molality goes to 0, the activity is going to be related with that molality, okay, divided by 1 molal, since again, it's a unitless quantity, and your activity coefficient is just going to go to 1. Okay, so same type of stuff for the limits in an ideal dilute solution. Any questions about kind of these definitions of activities, formulations?
So that's mu B naught prime?
Yeah. Which again, like later we might just call it like mu B naught or mu B. It doesn't really kind of matter the symbols that it's given. It's like this reference chemical potential that we don't really care about what the actual reference chemical potential is, right? We're often just concerned about how it's changing with something, right? But yeah, that's supposed to be mu B naught prime, right? We had mu star, which is the pure solute chemical potential, right? Then mu naught, which was that solute chemical potential modified by Henry's law constant, and then this mu naught prime is the solute chemical potential modified by Henry's law constant, modified by some molecular weights and other things like that in order to change things into molalities from mole fractions. And we could, work all that out if we wanted to in kind of more detail, but it's not too relevant. All right. And the last kind of thing we talk about with these activities is fugacity, okay, which is the activity for gases. Okay, I don't know why it's not called still just activity, but whatever, it's called fugacity, right? Legitimately, what is this called? Fugacity. Okay. And the fugacity is essentially the effective pressure of the gas, of a real gas. Okay, so the chemical potential, right, of an ideal gas is just related with RT, the natural log of that pressure, divided by, say, 1 bar, right? Assume the pressure is measured in bars, right? That's the chemical potential of the ideal gas. For real gas, it's the exact same formula. You just replace the ideal pressure with the fugacity, which is the effective pressure of that gas, right? Let me click here. I'm missing a thing, right? And that fugacity is defined as the fugacity coefficient phi times the pressure of the ideal gas. So P here is the pressure of the ideal gas, right? And phi is then this fugacity coefficient, which describes how that pressure of the ideal gas deviates from the real gas, which, to no surprise, is related with the compression factor, right? Because the compression factor also tells us how the pressure or molar volume deviates from the ideal case, right? Right. So Z, right, in this formula for the fugacity is defined as the the compression factor for a real gas, right? Right, and if you remember, right, if Z is equal to 1, over all pressures, that means it's an ideal gas, right? And then you get 1 minus 1, which is 0. So the right-hand side of this equation equals 0, and the natural log of 1 equals 0, so phi equals 1, and therefore the fugacity equals the ideal pressure, right? So it all kind of works out, right, that if z is equal to 1, F equals P, right? Fugacity equals your ideal pressure. Okay? But if Z is not equal to 1 over all those pressures, right, then it's potentially different, right? But yeah. Okay. So again, the fugacity is essentially the activity, but for gases, right? Activity was the effective mole fraction. Fugacity is the effective partial pressure, right? Or pressure of your gas. But again, both the approaches of both these things is, let's take the ideal case and just kind of multiply it by some factor, some number that accounts for the deviation from ideal. Now, again, that number isn't necessarily a constant, can be, and can be over a certain range, right? But technically, phi here, right, given this formula, definitely could not be some constant, right? Depending on z, depends on pressure and temperature and volume and things like that, right? This phi here could be related with volume and temperature or something like that, right? Yeah. Right. So if I use my compression factor was like 1 minus b prime p or something like that, right? You know, I can calculate what phi is for, say, a virial gas. Okay, and I guess you potentially won't get effective dependence on temperature, but it will depend on these coefficients, the virial coefficients, right, which do depend on temperature and the identity of your gas and things like that, right? So, but yeah. So again, these activity coefficients and fugacity coefficients don't have to be a constant. We'll often treat them as a constant and just assume they're constant for whatever problem we're dealing with, right? But they don't have to be. Yep. So questions about any of these things: fugacity, activities, for solutes and solvent. So for solvent, the activity is what? Is it equal to P of A divided by X of A, P A star? Is it equal to gamma A, X of A? Just one of them, two of them, none of them. So B here, people saying, yeah, so most people saying B here, so only 2, right? The activity coefficient times the mole fraction. And that is definitely true, right? The activity coefficient times mole fraction equals the activity, okay? Right? Expression 1 here does not equal the activity, right? That is correct. So B is the correct answer here, right? Because that right, the activity is defined as the pressure of your mixture divided by the vapor pressure of your pure solvent, okay? And so throwing in that factor of the mole fraction in there means that that term actually equals the activity coefficient, not the activity. So equation 1 is equal to the activity coefficient. Equation 2 is equal to the activity for the solvent. Okay. All right. So vapor pressure of pure water at 298 Kelvin is 23.76 torr. The equilibrium pressure of a 1 molar aqueous ethanol solution at 298 Kelvin is 22.55 torr. It should be more explicitly stated, right, that is the pressure of water in that mixture, right? So 22.55 is the vapor pressure of water in that mixture of 1 molar aqueous ethanol. Okay. I know it's not phrased in that way, but that's what it's trying to say. The question is, what is the activity of the solvent in solution? Sorry, that wasn't one of the answers. I don't know. Got some A's here. Right. So the activity, right, of the solvent is just defined as its vapor pressure in the mixture divided by the pure vapor pressure, right? Which again, I was trying to emphasize, right, that 22.55 torr is the vapor pressure of the solvent in the mixture. Okay. Right. So the activity is just 22.55 divided by 23.76, which ends up equaling a 0.95. Okay. Questions? Okay. For an ideal solution of two volatile liquids, A and B, the observed vapor pressure is 70 torr. What is the mole fraction of A in the solution, where PA star equals 125 torr and PB star equals 46.3? Okay. Again, we're dealing with an ideal solution here, and 70 torr is the total vapor pressure. Okay. All right. So we have a mixture, right, of two ideal, an ideal solution, right? Which means if it's an ideal solution, right, that PA equals XAPA star and PB equals XBPB star, right? We know these things because, again, it's an ideal solution, right? That's what we're told. We're told an ideal solution, so we know those are true, okay? And we're given this information up top, right? And then we also know, right, for any gases, right, the total pressure is just the pressure of A plus the pressure of B, all right? And then what we also know for a binary mixture, right, that say the mole fraction of A equals 1 minus the mole fraction of B, right? And so these are the things that we know for a ideal solution mixture of two species, right? And the question is, right, I think the question was, what is the mole fraction of A or something like that, right? Okay. And so, right, we kind of look at this and say, okay, well, mole fraction of A, I can get that if I know what PA is. I don't really know what PA is, but I got this equation here, right? And if I use this, and if I, right, I don't know what PA or PB is, but I know what PA star and PB star is, and I know P total, right? So if I plug in P total and I do XA PA star plus XB PB star, right? This is true for an ideal solution, okay? And then again, we're asked for the mole fraction of A. Is that specifically what it was? Yeah, right? So actually, I don't want to use this form of this equation, right? Instead, I want to say XB, right, is equal to 1 minus XA, right? Because then I can use this substitution in this equation to get that P total equals XA PA star plus 1 minus XA PB star. And now we're given everything in this equation except XA, and so we can solve for that, right? So this is 70 equals XA times 125 plus 1 minus XA times 46.3, okay? And so, right, this is something like 70 minus 46.3 equals 125 minus 46.3 XA, right? And so we just divide that over, divide this onto the other side to get the answer. Okay. Yeah. So I was going to go back to slides here, right? Yep. So XA here is 0.301, right? Right, so 125 minus 46.3 gives us 78.5. And then when we subtract 46.3 onto the other side, we get 23.7. And then 23.7 divided by 78.7, right, gives us 0.301. Okay? And we should expect that the mole fraction of A is less than 0.5, just because, right, if we compare the total pressure of 70 to the pressure of A star, right, or pressure of A in the pure mix in the pure solution, or not solution, right, but pure solvent, right? Pure PA, right, is 125 torr. Pure PB is 46.3 torr, right? 70 is closer to 46.3 than it is 125, right? And for an ideal mixture, right, it's just a linear change from, say, PB star to PA star as the mole fraction changes, right? And so you should expect that mole fraction to be less than 0.5 at least. Okay. All right. Any questions? All right. I have a non-ideal solution of two volatile liquids, A and B. I have a vapor pressure of 832 torr. Again, that's like it's the total vapor pressure over that mixture, right? I know for the solution, YA equals 0.404, XA equals 0.285, PA star and PB star are given 591 and 503. And the question is, what is the activity and activity coefficient of both A and B? Yeah, no, Y, right, so as a reminder, right, YA is used for the mole fraction in the gas phase, XA is used for the mole fraction in the liquid phase. Now, that's not me just being lazy about writing gamma versus. All right, so, right, so what we're given, right, is the total vapor pressures of the pure compounds A and B, right? And then what the mixture is in the gas phase and liquid phase of this real solution, okay? And then again, what the question is, what is the activities and activity coefficients of these different things? Okay. Right. And so, right, for example, the activity of A, right, is again defined as the pressure of A over PA star, right? But the question is what is PA? And how might I be able to get PA? So XA times PA star would be true for an ideal solution. In this problem, we're told we're dealing with real solutions. But what do we know about, there's a very similar formula to that one, to Raoult's law, that works for gases.
Is it like the Dalton's law of partial pressures, like the mole fraction of the gas in the vapor times the total pressure?
Yeah, YA times P total equals PA, right? The mole fraction, right, in the gas phase times the total pressure equals the pressure of that gas, okay? And so, right, so I can use this to solve for PA. So it's just 0.404 times 832 will give me what PA is, okay? Right? And then once I have that, I can plug that into the activity, right? So that the activity of A is equal to the pressure of A, which is 0.404 times 832, right, divided by PA star, which is 591. Okay. So that is the activity of A. I'm going to flip back over to the slides real quick just so I can get some of these numbers. So PA ends up being 336.14. And the activity of A ends up being 0.569. Okay, let's flip back real quick. This guy, okay, right? And so that's our activity of A, right? And then I can do the same thing for B, right? But first for B, I just got to find out what YB is, which is just 1 minus YA, right? Which is just going to be 0.596, okay? And so again, then PB is equal to YB times P tot, which equals 0.596, assuming I did that subtraction correctly, okay, times 832, okay? And then the activity of B is then again going to be the pressure of B, which is at 0.596 times 832 divided by PB star, which is 503. Okay. And so those numbers come out to be PB is equal to 495.9 torr, and AB is equal to 0.986. Okay. Yep. Okay. Right. And so this is the activity of B. Right. This is the activity of A. Okay. And so then to finally get the activity coefficients, right, those are just going to be, right, the activity coefficient of A is just the activity of A divided by the mole fraction of A in the liquid phase. Okay. So that's just going to be 0.569 divided by 0.285. And the activity coefficient of B, right, is the activity of B divided by the mole fraction of B in the liquid phase, which is 0.986 divided by 0.715. Okay. And then those, oh, sorry, that's kind of off page here, right? And so then those come out to be 2 and 1.38. Okay. The activity coefficients, right, for A is 2 and for B is 1.38. Okay. So questions about this problem? About what we did, why we did it, how we did it? Okay. All right, and that's actually the last example for today. So like I said, today is probably going to be a little bit of a shorter day. But yeah, so any questions about activities, activity coefficients, fugacities? Talk plenty more about this, right? On Monday, we're going to be, see here, talking about activities in ionic solutions. Actually, I already talked about the phase rule. But yeah, so we'll probably, Monday we'll probably just focus on activities in ionic solutions. And then after that, we'll move on to two component phase diagrams and then chemical equilibrium. Right? We'll eventually get to electrochemistry and stuff like that. Right? So as of now, we're about kind of a week ahead of my rough estimation of the schedule, which happened actually last year as well. And I just didn't bother updating the schedule. And I should have. But basically, the plan is in some of those extra days that we have, we'll talk a little bit about statistical thermodynamics and some of those things. Okay. And so, right, there's not really any time set up in this semester or next semester to talk about statistical thermodynamics. And so using some of the extra days, we'll kind of introduce some ideas behind those topics and things like that. And basically talk a little bit about how using statistical thermodynamics, you can take the things that are determined and discovered and predicted from quantum mechanics and use that to derive all of the thermodynamics that we've talked about. Okay? So you can get all of these relationships with internal energy and enthalpy and Gibbs free energy and chemical potential and entropy and all this wonderful stuff from essentially quantum mechanics and the energy levels and other things predicted out of quantum mechanics. You can use those to derive all of the stuff that we've talked about this semester. Okay? And we'll talk a little bit about how that is able to be done and things like that near the very end. Okay? But yeah, otherwise, no questions. Then I will see you guys on Monday. Okay, which again, I should have the exams finished by Monday. I will have at least started grading them, but I should have them finished by Monday. That's also grade some Gen Chem exams, but those it's mainly multiple choice, and so there's not too much grading I have to do for that.
I'm okay with
Enough. Talk to people who've taken this class and had to take the ACS final and ask them how they felt about the ACS final compared to the regular exams. So.
It's just a final by the American Chemical Society.
Yeah.
Yeah.